Hello everybody, my name is Thomas Richter. I work for IBM Research and Development in the Linux Technology Center, and we are going to talk in this session about software-defined networking using the VXLAN device driver. The agenda will be centric on the VXLAN device driver. It's an IEEE draft, IETF draft, and also an RFC standard. It had been released into the Linux kernel late last year, and so a couple of extensions is the Linux 3.8 kernel, the so-called DAV extensions. The DAV extensions stand for Distributed Overlay Virtual Ethernet and are basically add-ons to the VXLAN driver to actually really use it for for software-defined networking. So I'll show you a little bit about the VXLAN details. We need that for the next item, principle of operation. So we are going through a few examples on how we create, migrate, and delete virtual machines. We go through some examples, advanced usages like multicast, broadcast, detection of VMs. And then finally, we talk a little bit about the management tools we need to get actually the most benefit of our VXLAN defined networking. And at the end of the session, if we have time, I'll have a few words about Relation and future work. Okay, so where are we at right now? Data center virtualization. So we have a few hosts, A and B for example, and the customers run virtual machines on them. Big data centers have a lot of customers, and we see them, they are separated using virtual machines in different colors. So this is quite standard now. What they really want is the customers are basically a network which really belongs to themselves. So they share an underlying network right now, and what we really want is their own logical network. This own logical network can have individual address spaces for IP and MAC addresses, so each customer might have its MAC address and they might be the same as a different customer will have. Of course, the connections should be no interconnections with other customers as well, so the logical network should belong to me. And what this really refers to is an overlay network. I want a logical view of my network on top of an existing underlying network and use the existing underlying infrastructure. Okay, what we want really is a central management and control. So the customer would like to be able to control his logical network. It should be reliable, of course. And ideally, it should cover long distances. So it doesn't really matter if the two data centers or the two machines are next to each other in one room or if they are across the globe. And optional, if we want to have the ability to find policy. So for example, a specific machine shouldn't be able to talk to another machine, for example. Or if we go across a long distance network, we might want to actually chuck in an app which does encryption for us before it goes onto some unknown service provider network and will be decrypted on the other side when it receives our destination virtual machine. Those are the needs for the customer, and I'm going to show how we can realize that using VXLAN. Okay, VXLAN is shorting for Virtual Extendable Local Area Network. It basically operates by encapsulating data. So the data leaving the virtual machine is encapsulated, distributed, sent over on the internet. The participating hosts, which are called virtual tunnel endpoints, and the virtual tunnel endpoints are interconnected using standard IP infrastructure. VXLAN provides a 24-bit network identifier. This is prepended every packet leaving a VXLAN device driver. This defines what we also call a VXLAN segment. So the idea is that a virtual machine can only communicate with another virtual machine if they are in the same VXLAN segment. So in different VXLAN segments, can be used at the same IP and MAC addresses in different LAN segments. And also very important is the virtual machines are unaware of the encapsulation, so there's no need to change anything in the software stack. Good. I focus on the recent extensions and the typical flow scenarios why we have implemented them and put them into the latest kernels. I show you the mapping of virtual machine addresses to the destination endpoint, so the virtual machine knows where to send the traffic to. And of course, very important is the management of the virtual tunnel endpoint. So we are going to talk about these items. But first, I have to talk a little bit about VXLAN so that we are on the same page. If you create a VXLAN device, you create it usually on top of some physical Ethernet device. Pretty simple. We have two hosts, A and B. My VXLAN device are named 2000A and 2000B, and underlying Ethernet devices have some weird IP addresses. Doesn't really matter. What will happen is you created this VXLAN device, and this is a command. In here is ID 42, meaning this is the network identifier we are going to use to actually talk between my tunnel endpoints here and here. And the next thing is we specify some weird IP address. This is a multicast address. What will happen when the VXLAN device driver is created? It will happen two things. First, it creates a tunnel endpoint. The tunnel endpoint has a port number, so it is a UDP socket endpoint. Port numbers in the kernel right now are 8472. It doesn't really matter. The IANA assigned number has been set to 4789. It doesn't really matter. In the Linux 3.8 kernel uses this one and later ones as well. The next thing is we join a multicast group. This is needed for actually sending out the packets. And whenever a packet goes down there, we encapsulate it with this VXLAN header. What is in there, I'll show you in a second. And it goes over the network, and the receiving side receives the encapsulated packet, takes out the header, does some checking with it, and moves it up to the receiving device driver instance. And here you can see we have the inner packet. For example, if we do a ping, then we have this inner packet from the VXLAN device, a VXLAN header prepended, and then we have the outer packet for the transmit over the infrastructure of IP. Okay, some more details on it, unfortunately. What will happen if, for example, we have our two hosts A and B, and I want to send on host 2000A a ping packet to host 2000B. So I'm on a virtual machine. I use my logical network, so I know nothing about the underlying infrastructure. So the first thing which is happening is, of course, that we don't know the destination MAC address. 2000A, 2000B is unknown. What do I do with it? So next thing is I send out an ARP reply. An ARP request. Okay, so this is now hitting the VXLAN device driver. It doesn't know what to do. The only thing it knows to do is that I had to prepend a VNI number in this VNI header here. Okay, it will do so, and then, well, there was this multicast address when we instantiated this device driver. Okay, since there's nothing better to do, we use this multicast group and send out the data packet on the wire. Host B, having done the same thing, will receive this multicast packet. Okay, we'll find out that there is a VNI header, and it will look at the VNI number we instantiated, or we used when we instantiated the device driver. And hopefully it will be the same, then it will accept the packet and route it onwards to the VXLAN device driver. This device driver is pretty happy because it can answer the 2000B MAC address request. Okay, we could do the same trick, so put in an ARP reply, do out the multicast, and all the thing goes back to host 2000B. But we could do better, because when we receive this packet here, we have two headers actually. We have the outer header, where we have the source IP address of this sending tunnel endpoint. The next thing we have is we have the source MAC address of this sending endpoint. So we can actually combine those two values together, and we know that we want to send something to 2000A. Okay, this guy was kind enough to send us our MAC address. so we know where to send the MAC address to, and we now have the destination endpoint because the packet came from this guy. So we know host A is the one actually hosting this virtual machine or this network endpoint. So what will happen is that instead of sending back a multicast packet, it will send back a directed unicast packet and saying, okay, I know where you are, here's your ARP reply. Okay, so we hit one of the main things of the VXLAN device driver. It's a so-called forwarding database. The forwarding database is responsible for knowing which MAC address is actually hosted by a certain tunnel endpoint. So it's a mapping between the destination MAC address of this guy and the tunnel endpoint, which is the source IP address of this guy, or IP address of this guy. So this forwarding database is actually can be shown using a new command in the IP tools chain, or IP route 2 tools chain. It's called bridge forwarding database show, and there you can see all the entries from the VXLAN device driver. In this case, for example, we have the source, the MAC address of the host in 2000A, and the destination to send it to is 192 and so on .a. And then last line here, we see the catch-all MAC address of 0 is invalid. Does mean in this case, if we do not know where to send the packet to, well, we go out and send it on the multicast group to actually make sure everybody in my network receives the packet and has a chance to reply to it. So it's a so-called catch-all. So this is the status of the VXLAN device driver, how it was introduced late last year, early this year. And when we want to use that for overlay for network system, for software-defined networking, this device driver lacks a few features. So the drawbacks are pretty simple. I want a control plane. So if I want to control which machine is part of my logical network, I really don't like the idea everybody plugging into a multicast address. Now we want to actually have a central point of management to allow hosts participating in my logical network. Next thing is multicast routing. So if you span the globe, you rely on a long path, but you cannot be sure that every hop in between is actually supporting multicast routing. In fact, a lot of vendors don't do that, so your packet might get dropped somewhere in between. Next thing is multicast addresses are pretty limited, so we don't have as much multicast IP addresses as we want VNI numbers. Because if you are talking about logical networks, you can use VLAN. VLAN has 12-bit, so it gives you 44,069. This number can be up to 24-bit, so it would be 16 million logical networks, but you don't have 60 million multicast addresses, so that's not going to work. Okay, what went into 3.8 DAF extensions? The first thing is what we call an else remis. Else remis means if I want something to send to a destination IP address, I need some help. The help is the ARP request to find out the destination MAC address. We don't do that anymore by sending the multicast packet, but we trigger a let link message from the VXLAN device driver to some, let's call it user space helper or helper program, asking for help. There's a destination IP address I don't know, so tell me the MAC address. So what is expected? Well, it is expected that this user helper program will send us a reply in form of an entry in the neighbor table. So the idea is that I don't know a destination IP address, give me the destination MAC address. If I don't know a destination MAC address, give it to me and please enter it in my neighborhood table. Okay. Let's call the L3 miss. The L2 miss, we have a MAC address, but we don't know the corresponding tunnel endpoint. Okay, so we need some more help again. The idea is again not to do a multicast, but to actually ask our user space helper program, which tunnel endpoint is it? And the expected action from the user space helper is a netlink is a reply in form of a command to actually enter this correct entry in the forwarding database of the VXLAN device driver. Okay, then next feature we have added is no learning. I just introduced you to the idea that the ARP reply is done by unicast by investigating the inner and outer header. We don't want that in a user-controlled environment, so actually we disabled that type of snooping. And then we put in some optimizations, proxy and route short circuiting. That's important, or well, it's not really important, you can live without it. It's just some optimizations if the VXLAN device driver is used in an outgoing interface of a Linux bridge. Then the proxy reply is, the proxy command is there to actually send out the ARP reply by the VXLAN device driver if it has a mapping instead of sending it to the destination machine and back again. And short circuit cutting if needed if you use virtual machines as a router. If you have time at the end, we might come to that. It's just an optimization to save the first hop. Okay, so the key point in the VXLAN device driver is its forwarding database. It has keyed by destination MAC addresses. So it has a unicast MAC address. In this case, we only have one single entry because we have one single endpoint. And the information contained herein is the destination IP address, a VNI number, and the port number in case for some crossover talk. We come to that later. So this is just a mapping where to send the packet to. More advanced is multicast and broadcast. What will happen in this case if we do a multicast or broadcast, that we have several recipients of each packet. So the VXLAN device driver knows which tunnel endpoints need to receive those multicast packets, and it will copy and create a packet outgoing for each destination. So it does a lot of copying and will send all the packets in parallel to the destinations. Those here in blue are add-ons basically done into the 3.8 kernel to support the DAF extensions. And of course we have commands in the IP route 2 toolchain to actually create an entry. This is bridge FDB add. To delete an entry naturally, this is delete. Append if we have a multicast MAC address, so we want to have multiple destinations. And replace is just an optimization. Put on if you change the destination endpoint, we ended up deleting the old entry and adding the new entry, and that was a bit of a caused a few race conditions, so we added the replace command to actually update this atomically. Good. What is this all good for? Let's go through a few examples on how we actually use VXLAN in reality. So this is the command to actually instantiate a VXLAN device driver. As you can see, there's no multicast address anymore. We have the network ID. We use L2MIS, L3MIS, some optimizations and no learning. So what will happen if VMA is going to send out some packet down to VMB? Okay, first of all, it wants to know what is the destination MAC address of 2000B. Okay, at the initial startup, we don't know. What will happen is we see this L3MIS message coming along. The user space helper is hopefully around, and actually will put in an entry into the ARP table and telling us, okay, you have to send, this is the MAC address of this target guy. Next thing is the packet is then routed further to the VXLAN device driver, and he will ask its database where to send data for this target MAC address to. The database initially is empty, so we'll see an L2MIS message saying, okay, where is the tunnel endpoint? No problem, somebody will fill it in for us, and the data is sent, the packet is sent to this target device over here. Again, on the B side, or host B, the setup was done in a similar way. No problem, this guy will receive the information and will send it back. And this is how we actually set up our virtual machines. We are using a virtual bridge connected via MacVTAP, and the only underlying device is the VXLAN device driver. Okay, and once both tables are set up correctly, traffic between VMA and VMB can flow, and it doesn't matter if you go across the globe or just two boxes next to each other. Okay, so simple situation. Now let's get it a bit more complicated. Assuming we have our two machines again, and we are migrating VMA from host A to host C. Nothing really changes. I mean, what is happening is that we have to delete the forwarding database entry on host A. It's pretty simple. Next thing is we have to copy the database entries forward to host C. It's also pretty simple. Notification, we use libvirt and QEMU, so the libvirt migration events can be used to detect that. But there is a disadvantage. There are many other hosts which might not be either the target host or the migrating from host of this migration. So the other hosts in the network have to know that the destination endpoint for this guy has changed from host A to host C. So everybody participating in my logical network has to be made aware that the destination endpoint of virtual machine A has moved. Okay, this is something we'll come back later, but this is the basic idea. By simply manipulating those entries, the virtual machine A can talk again to virtual machine B. And next thing is pretty easy task. We remove a virtual machine. This is really daunting. Again, we just simply delete the entries in the forwarding database from host C. And more complicated, of course, all the other network participants have to be notified, and the forwarding database entry has to be deleted, so this guy cannot be reached again. Good. VXLAN supports broadcast and multicast as well. So let's assume we are running on host A and want to talk to host B, or VMB and VMC. The entries are pretty simple, they are the same, but this time we have to talk from host A to host B and to host C simultaneously. So if you run a ping and you do a broadcast ping, your destination MAC address will be all Fs. Okay, what we need is basically some mapping in my forwarding database to actually find out that if I talk to destination MAC address all Fs, I have to send the packets to several destinations. And the destinations are also participants in my network. So by some kind of magic, somebody is going to actually add those entries for me if I do create virtual machines. Good. Next thing is the multiple customer setup. Assuming we have several...
When you talk about the migration, the way hosts which were aware of the previous address are notified, you didn't mention it.
I come to that later when we come talk to...
later, you're going to talk about that.
Yeah. I'm just laying a little bit of ground rules, so we are...
It's a ground for that.
Okay.
I'm also having a question. It's possible to go
One slide back.
Yeah. So,
Oh, sorry, that's one slide forward.
okay. So if you know multicast and you want to send a broadcast from the upper level and you don't have an FFF entry,
Yeah.
it won't send that packet. It will send a netlink message to users. That's what it will do in this case.
Right. Or for example, when you create the virtual machines, you know what are your other target endpoints, and you can create those entries in advance. Okay, so let's go and talk about our multiple customer setup. So for example, here again we have several customers, the red one and the blue one, and both have the same setup. We use a virtual Linux bridge, and we have two device driver instances of the VXLAN device driver. And again, we have the same on the other side. So what is happening now is that you have to actually make sure that one side of the VXLAN device driver, so for example, if you talk from VMX, it goes down to this bridge and down to this VXLAN device driver instance. And down here you see a virtual network number 4. So this is the virtual network number the VXLAN device driver was instantiated with. So if it's going outbound, so the traffic will be prepended with this VNI number, and it will travel through this network on the other side. So here it will be received by the VXLAN device driver, and it will check out the header. So if the header number is 4, it will be going out to this instance, and it will be going up to this guy. So it will be falling up to this bridge and to those virtual machines. And on the other side, if you are going down to this path, you are using a different instance of the VNI of the VXLAN device driver, and you have a different network number, and it will go out on the physical interface and will be received again by this side or this side. What is it? You send it out 4, so we go up to this side, and it is the receiving guy. So the VNI number in this header of the VXLAN device driver is actually the fan out to make sure the traffic is not interfering between different customers. What can also be done, and this is something we call logical network traffic or cross-logical network traffic, is that we can define so-called domains. A domain is a set of logical networks under one central control. So what will be possible is, in this case, for example, that I have an entry in this forwarding database, and I want to send traffic from this machine using VNI number 3, and then I will target this machine, for example. This is 2100B. So the idea which is that we have an entry in the forwarding database or in the ARP table that we want to talk to this box. So we do the mapping between the IP address and the destination MAC address. And now we have this entry in the forwarding database, but now we have an additional entry called VNI number. This means when the traffic is leaving my device driver or my VXLAN device, instead of using my default number 3, it will go out on the wire with a header put in VNI number 4. So the receiving side assumes that the traffic was sent from VNI number 4, and it will go up this path, and it will actually enable us to talk from red to blue. So this is the way we could support cross-logical network traffic if we want to. That's not the default. You have to actually put it in and make the forwarding database entry accordingly with your IP route command or IP bridge command. But if you want to, you can do it. And again, then we have here a different net than here, so we can also use the standard routing tools to actually do IP routing. Good. One last thing is there, then we are through all these scenarios. You want to sometimes talk to external connections. So what we can do is basically, and what we will do is, we have a virtual machine, for example here, going down to this path, talking to this guy. And this guy has now two connections. It's called a gateway. One side of the connection is basically attached to my logical network, and the other side of the connection is a MAC-VTAP device attached to, for example, a network NIC or some other Ethernet device which is connected to the internet. The same trick can be done if you want to talk to via this gateway from the MAC-VTAP device to the underlying network. So we are actually having a connection from here down here, and then we go back to the underlying network, and then we can talk to VM2, which is on host B, directly connected via a MAC-VTAP interface to the physical NIC. This is how we can set up the connections between external internet and the underlying physical network. Okay, so those are the ground rules. What really do we need this for? Okay, I have missed so far one thing, is the point that we need some aid to actually define the logical network. So, as I said in the beginning, we had this anonymous user space helper program. Well, what's the idea behind this? The idea is pretty simple. We have on each machine, which is basically part of our logical network, a tool running called agent. The agent is there to actually manipulate the forwarding database entries and the neighbor table entries for the VXLAN device driver. So the idea is that every agent, that every host which participates in our logical network has such an agent running. The agent is responsible for actually detecting that the virtual machine is started. This can happening via at boot time via, for example, a DHCP snoop, so a virtual machine boots, attaches to the Linux bridge and gets via DHCP its IP number.
When you say gets VM, IP, and MAC address, you mean it learns it? It doesn't get it from that administrator?
Well, there are two ways. You can actually define on the Linux bridge IP addresses which are assigned when you start a virtual machine. So
no. Let's say it goes to an external DHCP server.
Okay, we haven't done that, because what we have done is we attached it to the bridge and we used the bridge to actually reply with the DHCP and supply the virtual machine with an IP address.
Because in Open vSwitch you can register hooks that it will give you.
Okay, no, I can't.
Anyway, basically,
yeah.
It would be nice if the agent can learn that, correct?
Yeah, it will actually be able to learn that, because if the bridge is responding to the DHCP request with a DHCP offer, then the agent can actually snoop that in and learn it. The other possibility would be to have a static IP address of the virtual machine. In that case, we have normally a Graditus ARP. That's an ARP packet sent out at boot time to make sure my IP address is unique. So I send out an ARP and I do not expect a reply. So that means there are no reply coming in. I use this IP address because nobody else has a MAC address for it. So this is the both possibilities we can actually use to find out the virtual machine's data, like IP address or MAC address. This can be then forwarded to some instance I call agent manager. So the agent manager is in constant connection with its agents to actually find out which machine resides where. So it learns the information of VMA being started, and it will then know which other agents are around manipulating my logical network. So it will send this information back to all the agents in my logical network, and they will feed the corresponding entries in the forwarding database and in the neighborhood table. Okay, if the virtual machine wants to do multicast, it will also be possible, because the agent can do some IGMP snooping. So it will realize the virtual machine joined a multicast group or leaves the multicast group. And this information can then also be forwarded to the agent and distributed throughout my logical network. Okay, so the agent is the key point in defining my logical network. It is a connection to all the agents to actually make sure the data is shared and spread out through my logical network. Important program, so we have to make sure it is reliable. So the idea is to have multiple instances, basically master responsible for all the requests coming in and a few backups, and they control each other using some heartbeat monitoring. So if the master is dead, some backup will become master and take over. This guy can also be used to actually define policies. So for example, if host A or VMA should not talk to this VMB machine, the agent can simply deny corresponding entries. So the agent is then has to have the information which logical machine should be able to talk to which machine. And also, if the agent realizes that the destination is far away, it can also feed the corresponding information to the agent and tell the setup or make the setup in such a way that the virtual machine will send its data to some appliances, and the appliances will, for example, do some type of compression or some type of encryption if the network is going throughout a wide area network. And on the other side, the same thing will happen again. So this is the central hook to actually define your policies and to actually define your logical network. Okay, and as I said before, there's a constant data exchange between the agents and the agent manager, and the agent also hooks into the libvirt daemon to actually watch out for migration events. So whenever a machine is shut down for migration, the agent can notify the manager and telling the manager the machine is going down, it's migrated away, and on the other side the receiving agent can instantly notify the agent manager that the virtual machine is being received and is put back online. So it can feed the corresponding information to the forwarding database entries. That is the basic idea of the control plane for this type of logical network which we are using with VXLAN device driver. Okay, I'm nearly done. So what I have to say is we have a few details to tell about. So if you are using standard IP throughout, we are adding a little header. It's only 8 bytes. But those 8 bytes might be able to actually break your maximum transmission unit. So what we will do on the outgoing interface, that we make sure that first the header is that the header can be fitted into the outgoing packet by making sure the data is not larger than the maximum transmission unit minus the header. And then we set the don't fragment bit before we send out the packet on the wire. The tunnel endpoints connection is UDP only. That's not really a big bummer, because if your virtual machines are using TCP, the virtual machines will make sure they transfer the data reliably and consistently. So the virtual machine TCP stack will make sure the data is sent and received correctly. And the underlying traffic, if it loses a packet, well, tough luck, TCP inside the virtual machine will find out and will retransmit the packet, hopefully. And if the virtual machine is using UDP, it has some other way to actually make sure the data is transmitted correctly, because UDP itself is somehow not really secure. So you have to cope with data losses using UDP. The next thing is security. This is a bit more complicated, of course. The best thing would be to actually hack your agent manager and make him distribute the wrong entries. So there has to be some security put into the data manager to actually protect its database, so we can manipulate the database. Very simple would be actually to change the VMI number and just transfer the data as something totally different. We don't want that. So, and of course we have to have secure communication between the agent and the agent manager, also that the data to feed the database entries is not hacked on the fly. Next thing is if you employ some type of middle boxes, may it be virus scanner, firewalls in between, they don't know about VXLAN, so they have to know that there's an outer packet and there's an inner packet, and they really have to concentrate on the inner packet because that's the payload and not the outer packet. A few more things. IP version 6 support is currently, it's already in, but it's missing multicast support. So if you use the underlying protocol version 6 as an underlying protocol, you don't have the full function right now. IPv4 is okay. As I said, it's kernel 3.8, but if you want to try it out on your own, 3.10 is better because we put in some fixes recently. So if you are using IP tables, EP tables, traffic control commands, you can do anything on the host. It's all without VXLAN, because if you are manipulating the outgoing interface, Ethernet interface on the host, there's nothing you see. VXLAN is completely hidden in this level, so you can use those programs as today. We have some alternatives. For example, you can use VLAN. For those you know, VLAN is this 4-byte header inserted by hardware. So if you want to use VLAN, you have two disadvantages. First, your network range is limited to 4090, something like that, because you only can use 12-bit out of your VLAN header for logical networks. And of course, you have to make sure it's enabled all the way from source to destination.
No, you can enable it only on the switches if they walk in access mode.
Okay, but it has to be enabled to the destination as well, right?
Yes.
Okay. Good. The next thing is there's an alternative standard IEEE 802.3 called QBG. Edge virtual bridging is something similar. It has a disadvantage that you have to configure your hardware accordingly. First of all, this is non-standard because it requires a switch being able to actually send the traffic back out of the same port it received it on. So this is an extra add-on. And of course, you have to configure your switch accordingly, and then the switch has a disadvantage that it sees all the MAC addresses from the virtual machines. So if you have a large data center with many virtual machines, your switch has the problem of a very large table size, and the resulting spanning tree protocol to actually remove redundant passes can become pretty large and slow. So this is a disadvantage of IEEE QBG. Okay, so let me summarize what we have achieved with VXLAN as a workhorse for my software-defined networking is we have independent addressing. We have location-independent addressing, so it doesn't matter where your virtual machine resides. It keeps the same IP address and it keeps the same MAC address, regardless if it moves one block or one continent, or it doesn't matter. You have a logical network which scales nicely. You have independent of the underlying physical network and protocols, so you can use any protocol you want in between. You can use the existing IP infrastructure in place today. You have no virtual machine addresses whatsoever on any external devices or switches or so on. You have no VLAN limitations, so the limitation is basically the number size in the VNI header, which is 60 million. That should last a while. And you do not rely on multicast routing. So that's another big plus point. And you have address space isolation. So if you're in your data center, different tenants or different customers have totally isolated network and can use the same addresses if they want to. So it's totally isolated. It's all done in software. You don't need anything to do in hardware. It's all by one device driver, which you have to actually insmod and attach it to your virtual bridge, and then you can use these features. Okay, so a few words about related and future works, and I'm done. It's basically, as I mentioned, an overlay transport protocols. There are a few others around. I'm not very familiar with all the other ones, I must say. They have the same concept, so it's an inner packet for the VM and the outer packet for the transport interface. We have network virtualization using generic routing encapsulation. It's been around for quite a long time, as you can see on the RFC numbers. Its main difference is that we use a dedicated protocol. VXLAN uses UDP, whereas they use their own protocol over on top of IP. That's all I can say about that. The next thing is stateless tunnel transportation, STT, specially designed for NICs which do hardware support for sending and receiving large buffers. So if you have a network card which can do transport segmentation offload or large receive offload, this protocol is actually used to use the hardware features to actually segment the packets into MTU chunks, transport it over the network, and doing checksum calculation all by hardware. That has to be.
But this can be done also for VXLAN in the
Can it?
In the upstream Linux kernels, there are a few drivers which know how to do that for the encapsulated traffic as well.
Oh, since when is that in?
Over the last months, there's
Okay.
Broadcom and Intel, and also Mellanox, our hardware.
Okay. Oh, that's nice to hear. Good. And future work, we are going to think about integration into OpenStack and maybe using OpenVStage instead of the Linux bridge we are using right today. Okay, so this is basically the end of my talk. If you have some more questions, I'm happy to answer them if I can. Yes?
Yeah, what does VXLAN bring to the table that VPLS hasn't had for years already?
Did what?
VPLS hasn't had for years.
VPLS?
Yeah.
Not. I'm sorry, I don't know much about VPS. So.
It's an application on top of MPLS that
Okay.
does pretty much exactly that.
Oh.
It's been around for 6-7 years. And
Okay.
quite
No.
widely deployed.
I'm sorry. I'm unable to answer this question. Maybe you can talk later offline, so you can maybe show me a little bit. Okay.
You usually use in software. You usually use in hardware. Lots of VPLS. That's usually the case.
Generally,
In
yeah.
order to use VPLS efficiently, you need to have the VPLS network underneath. You need to do the execution for the VPLS.
That's true. I mean, in the case of the virtual hosting, okay, yeah, you need some sort of host support, but this is the case for VXLAN too.
All this kind of technology, VXLAN, NVGRE, all these things, is what, I mean, for the people that are networking oriented, this kind of technology exists since many years. It's just the invention, if you leave it, the invention, the nice thing about VXLAN is that it can go through the firewall without any problems, because it's just over the if you have to use things like VPLS, VPLS, but if you need to go outside a segment, think that if you have to do travel over the internet, right? With VXLAN you can travel over the internet. With MPLS, with VPLS,
No.
Okay. Are there more questions?
The difference is that it runs directly over IP.
Pardon?
It runs directly over IP.
Yeah.
We have MPLS and
Okay. What other question are there?
What happens in the event of agent manager failure of isolation?
What happened in the event of?
The event of the agent manager failing or isolation of the agent manager.
So when the agent manager isn't able to provide the correct VNI number.
When it fails, when it can't be reached.
Oh, okay. So in case you don't have any backup, you probably won't be able to communicate. I mean, the existing communication will continue until the forwarding database entries will time out. So if the,
It's a constant communication
Yeah.
between the individual agents and the agent
it has to
manager.
be. I mean,
So what happens with the
well, I mean, the agent is basically notified when something changes inside the network. So if there's no change at all, the agent manager maybe must not be reached, because if you don't start a VM or don't migrate a VM, the agents have the databases already distributed to the VXLAN device driver.
can the agent manager be replicated? Can you have redundant?
Yeah, that's what I mentioned. Sorry, it went under. So the idea is, at least in our scenarios, that we have several of them. There's a master and a backup, and they are in constant heartbeat monitoring. So once the master fails, the backup will take place, and obviously you can have multiple slaves and one master or so. More questions?
What do I need to run this apart from the current Linux kernel?
You need nothing else. I have, in fact, running it on a bare Linux kernel, plus the I have for the virtual machines libvirtdaemon and the VXLAN device driver, and
you need the agent and the agent manager.
Yeah, where
Right.
do I get these
But-
from?
that's a good question. Now, this is something I can't actually much talk about. There are Yeah, I knew this question was coming. Let me refer to item number 2. So this is basically what we call a software-defined networking white paper. This is the state of direction where we are.
So the agent is not open source?
The agent is not open source.
You can run without the agent. It would work if you do multicast and learning.
Yeah, okay, but that's right. But if you don't want to do, okay, I've been notified. 5 minutes?
Was that?
5 minutes or stop?
There is an IBM product which is based on this agent, or it's only research product?
Just wrap it up pretty quick.
Okay.
If there is a product of IBM that uses this agent, or it's only a research product?
Well, actually, I can't say much about this, so this is all I can say. It basically answers the question, right? It's not just a research project. Maybe we can talk offline later on. Okay, so any more questions? I'm here around for the next 3 days, so if we have to wrap up, so if there's more questions, I'm around. Drop me a note, talk to me, maybe just right now. So thank you very much for listening to my presentation. I hope you got it.
All right, great, welcome. What we're going to be talking about today is the Nexus 9000 in Cisco ACI. What I want to be able to do is give you some idea of how I think about it. I'm a very strong UCS Nexus guy, and so that's kind of my background. Just FYI, currently not an employee of Cisco, Ensemi, VMware, or any of the partners. So with that in mind, let's go ahead and take a look at this thing. Now the 9000 is pretty impressive. Okay? And we're going to try to understand some of the different components that make it the cool platform that it really is. To do so, I think it's good for us to move back a little bit in time and remember that, okay, well, Ensemi, that's cool. Have they done something like this before? And so most of us will go back and remember that we did do something like this with Nueva Systems. When Nueva Systems come out, very cool platform, right? A lot of cool technology involved here. And what it did for us is they came out with a couple different platforms. The first one I'm going to talk about is the 5000 series. The 5000 series, all right, combined with the 2000 fabric extenders, really gave us some cool ways to connect to our servers. And so what we could do is I could take some 5000s. I could toss out a few 5000s here. Right. And then we could have our fabric extenders. I'm going to just keep my drawing reasonably small. All right, I'll toss another 2000 in there, another 2000. And with that, we can do some arbitrary. I'll dangle another 5000 over here. And let's put some servers up there. All right, I'm only going to put a couple just because it takes forever to draw. And so we'll stick a few servers there. And maybe on this last one, instead of having the external 2000 as a box, we'll use the one that's actually integrated into the chassis. And so we can have these. When we start to cable these, we had a lot of flexibility in our cabling. But I'm going to go ahead and I'm going to just cable these guys together very simply. And we can cable these together in a multitude of ways. I'll connect down some of these down to the servers. You know, we could do some multi-home stuff. We could do all kinds of cool stuff, right? And then finally connect down these. Now, obviously a simplified solution here, but it gets the idea. With the 5000 and 2000, it gives us great connectivity down to the servers. And the way that we configure these is kind of the way we've been used to. With this, we use the command line interface. We use the CLI. All right, and we would go config, we could do a config command and start configuring. Everybody was happy, and we used Nexus OS. NXOS, CLI configuration, very familiar. Fabric extenders were awesome, gave us some cool ways to reach down to our servers, but the configuration, if I wanted to add a 2000, I'd cable it up, and then I'd have to go and do a little bit of configuration so it would discover the 2000 and things like that. Very, very cool, all right? And so everybody got this pretty much right away. Everybody understood this. But remember, Nueva also created something else really important, and that's going to be the UCS. Now, the UCS had a very structured deployment. We'd have 2 fabric interconnects, right? And I'm only going to show the actual data paths. And we'd go connect down to our chassis. Now, our chassis had the fabric extenders. So it still was fabric extenders with computers, just like the 5000, 2000. All right, still fabric extenders with computers. And let me hop out of the way here. All right, 5000, 2000 with computers, but now it was a very structured. All right, And the way we'd go through if we wanted to cable this, we had a very specific cabling methodology. And so I'd go through and I'd start cabling these guys, just data cables. We kind of ended up which looks like a spine and leaf type topology. All right. And so this was very cool. If I added a new chassis, all right, the cool thing, what happened when I added a new chassis in, is I just put that chassis in, I'd run a couple cables, and when I'd run the cables, we would find that it would automatically discover the chassis for us. Again, kind of a spine leaf look there. And so we had this. The big difference wasn't just the hardware, because fundamentally, if you look at a 5000, all right, you know, you look at a 5510 versus a 6120 or so for a 5510, a 5010 versus a 6120, from the outside, they just look a different color. A lot of similarities, obviously, between the two platforms, but the way that you thought about them, the way that you implemented them, was completely different. And so what happened here? Well, between these two platforms, we had a big change in the way that we thought. What we did when we moved to the UCS is, okay, hey, instead of going through in our command line, we're going to start thinking about this completely different. Instead of thinking about it, we started thinking about the idea of having something called service profiles. Now, all right, well, now with service profiles, what we discovered was very cool here. I could logically define what I wanted to happen, the way I wanted the service to be. I create a logical definition, and then I could apply that logical definition down onto stateless hardware. And that was a big deal. Tasteless hardware, that's nice. All right, down onto stateless, can't spell today, hardware. Okay, big difference. And how did we configure all this? Through a GUI. Now, granted, you still have a command line where you can go there, maybe do a little troubleshooting and that kind of thing, but this was a GUI. We went to the GUI, we configured this, and we made this run. So this was a big deal for us. As we went from this, moving from this idea of command line configuration, where we could go through, connect the 5000 to 2000 down to servers, have a lot of arbitrary configuration, moving over to UCS, where now this is the topology, boom, 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 but we could go through in this topology, we could deploy servers rapid. It was so amazing. It took the compute industry, all right, the server industry, which was kind of commoditized, and actually kind of decommoditized it, where people were willing to pay more for this incredible solution that solved a lot of their problems. So service profiles, I was able to logically define a server and apply it down to stateless hardware. I really didn't care which blade it went to, as long as it went to a blade that could go ahead and run for me. If something failed, no problem, I could just move that service profile. We've moved from the idea of a server being tied to individual hardware and creating that definition. We separated out, we started using profiles. We wanted to logically define our scenario onto stateless hardware. Okay, enough about Nuevo. So now we move from there and say, okay, well, John, you've been talking a lot about Nuevo. What about, you know, I assume at some point you're going to talk about Nsemi. Well, you're absolutely right. So let's go ahead and start taking a look at Nsemi. Now with Nsemi, we're going to go ahead, we're going to talk about a couple products. Okay. We're going to talk about product X and product Y. All right, we're going to just give them kind of generic names for a second, and then we'll explain what I mean. So we have two products. We have product X and product Y. And with product X, what we can do there is we have switches. So we can go through, we can take switches. And with these switches, we can go ahead, we can create kind of arbitrary topologies. Okay. And then I can go ahead, I can put some fabric extenders underneath those. All right, and so we have, and I'll put another fabric extender in there. And so I can go through, and so with this first product, I'm able to simply go through and create my network, connect it together. All right, and I have a lot of flexibility in how I go ahead and I do this. All right, and so I'm going to go ahead. And so this is it. How do I configure this product? Well, the way I configure this first product is I'm going to go ahead, I'm going to use the NXOS. And I'm going to use the command line interface. So I'm able to go through and I'm able to configure this device. This is cool. Sounds familiar. Very, very cool. Now, granted, we have some awesome 40 gig stuff going on in the background. We have some amazing hardware, all right, very, very competitive with the other products out there. And when you take a look at the BiDi and all this other kind of cool stuff going on, granted, awesome freaking hardware, fundamentally what you're used to, all right, a Nexus switch. Then there's this other product, all right, we'll look at the product Y, where now we have to have a kind of a very specific topology, all right. So I start rolling out these switches, and I go ahead, I start rolling them out. I need a very specific, so I'm going to go through and I'm going to roll out some switches here. And as I start to put these switches together, all right, and let me go put a couple more fabric extenders. I'll put a couple fabric extenders down here. Put a little bigger topology. And I'll go through and boop, and connect these together. You'll notice as I start to connect these together, okay, with really bad drawing, that once again, it kind of has that spine and leaf look, right? So we have a spine and leaf topology here, cost topology. And then we still can connect down to our fabric extenders and all that kind of good stuff, all right? So product Y, though, we have kind of a set topology, a very specific topology that we lay out. But when we do here, we think about it completely differently. And so with this topology, we're going to stop thinking about individually configuring devices and log in. We're going to once again, all right, be able to do profiles. We're going to do something called application network profiles. We're going to logically define the needs of our application and push it down to stateless hardware. We're going to do this through a GUI. This sounds familiar, doesn't it? It's like, I've seen this before. Same idea. Revolutionary again, all right? And there's some amazing stuff in the way the application network profiles are defined. Really revolutionary in the way we think about devices talking to each other. That'll be another session. But here all I want you to know is you're going to logically define this, going to apply it down to stateless hardware from a GUI. Okay? Very, very powerful, ultra fast, incredibly simple to go ahead and deploy. As you want to grow, you want to add a switch, you just cable it up, boom, it's automatically going to add into the infrastructure. You're going to have centralized management of all these through something called an APIC, but I don't want to go too much there. I just want to get to the fundamental idea. Application network profile, a logical definition created in a GUI is going to be pushed down to the actual hardware. I say GUI, granted, there's all kinds of interfaces. There are tons of APIs you can do to do almost anything. You create your own tools to go ahead and do all this. But you'll see most of them are going to be using the APIC, but you actually have a complete open API where you can write code or write scripts or whatever you like. So this is very, very cool and very powerful technology. But with our application network profiles through the GUI, we logically define the application needs and we push it down to hardware. So what products are there? Well, this first product on the left is a Nexus 9000. 9508, 9504, 128, whatever. It's one of our Nexus 9000s. And it's running in XOS mode. Now, the cool thing that I'm able to do is with ACI, I'm able to upgrade a Nexus 9000. I get ACI from Cisco. I can actually upgrade and use the exact same physical hardware, but now use it in ACI mode. So this reminds me a lot of the UCS days, all right, where people, when UCS first came out, a lot of people were like, hey, what's going on here? Where's my command line? I want to go ahead and, getting used to the GUI, and the concept of service profiles was mind-blowing. Application network profiles is going to be similar. It's going to take us a little while to get used to this. But once you get this and you understand some things that this can do, in particular in managing your virtual servers and your physical servers on whether it's Hyper-V or VMware, it's a completely different way and a much more intelligent way in some ways to define application needs. Once again, these are my personal thoughts and opinions. I hope you got some good stuff out of this, and I hope to go ahead and catch you again sometime in the future.